Good morning. I would like to begin by thanking the organizing committee for the invitation to give this talk and apologizing for not being able to attend in person. So let's begin. The word paradigm is commonly used in epistemology of science, especially since Thomas Kuhn gave it its current meaning in the 1960s and 1970s, starting with the publication of his seminal book on the structures of scientific revolutions in 1962. However, it is not a simple term to define. For my part, I would say that a paradigm is an idea accepted so absolutely that it does not occur to us that it can be otherwise. In other words, it would be as if our brain is wired in such a way that it's nearly impossible to think outside those limits. Obviously, there are paradigms in all order of lives, but we will restrict ourselves to their application to the world of physics. There are always mad people, lunatics, or visionaries like Galileo, willing to question our paradigms, but the paradigm works like a boxer. Although the other way around, the more punches he receives and the more he resists, the stronger and healthier he becomes. Otherwise, it would not be possible to explain how the Ptolemaic geocentric model resisted for 2 millennia. Of course, paradigms come in different sizes. For example, a very strong paradigm would be to say that the causes precedes their effects. Continuing with our boxing metaphor, this paradigm would be of a heavyweight division. If someone wants to convince us that it is not valid, he or she would be questioning our very understanding of reality. There are other paradigms that militate in the welterweight division. For example, that in quantum physics, it has no meaning to assign a trajectory to a particle, even though for more than a decade there has been experiments that contradict this statement. Very few colleagues are willing to accept this falsehood, and even those who already do so reluctantly. Finally, there are lightweight paradigms. For example, in our area of research, we assume without question that cross-sections are all that there is to be measured and calculated, when in reality, cross-sections are only the diagonal terms of a huge matrix. Outside the diagonal where cross-sections live, there are complex quantities that can be measured and are meaningful and important, but of which, in the worst case, we ignore their existence, and at best, we do not pay attention to them. In very few opportunities, a paradigm is overtaken by the evidence against it, and then, as Thomas Kuhn taught us, science becomes extremely interesting. When a boxer falls for knockout, an era of normal science ends, and a scientific revolution begins. This is called a paradigm shift. Here, I would like to review some few paradigmatic assumptions of atomic collision physics. Of course, I am not trumpeting a revolution, as these are flyweight and amateur category paradigms, but I think it's good to review them to at least be aware of their existence and wary of their implications. Let's start by going to the roots of these ideas. That is, like in a journey in the time tunnel, going back to the moment in the history of atomic physics almost 70 years ago, when one of these paradigms was first phrased by this physicist who possibly is not familiar to most of us. His name was Giancarlo Fick. He was one of those morally healthy physicists of the 20th century, and as one of his friends, Viktor Weisskopf, used to say, lived a happy life in a dreadful time. He was born and studied in Torino. During his youth and his entire life, he was actively against all forms of totalitarianism. Here we see him posing with some other renowned anti-fascists. He received his doctorate in 1930 and later spent time in Göttingen and Leipzig. He became good friends with Werner Heisenberg, with whom he shared a taste for classical music, mountaineering, and table tennis. In 1932, he joined the famous group of Enrico Fermi in Rome, I ragazzi di via Panisperna, that is, the boys of Panisperna Street. Here we see him, Fermi, and Amaldi spending some time in Ostia in 1836. His memoirs of I ragazzi di via Panisperna were published in September last year. It is a very interesting and enjoyable book, also in Italian, of course. In 1846, He followed Fermi to the United States, first to the University of Notre Dame and then to Berkeley. By 1949, anti-communist pressure has escalated, and all Berkeley appointees were required to disavow the Communist Party. Giancarlo was as far of being a communist as he was of being a fascist, and declined to take the oath. Due to this decision, Ernst Lawrence expelled him from Berkeley with the following outburst: "Get the hell out of the rat lab." Luckily, he quickly found work at the Carnegie Institute of Technology in Pittsburgh. In his old age, he returned to his hometown, where he died at the age of 82. Today, he is recognized for his work on quantum field theory, such as Wick's theorem of 1950 or Wick's rotation of 1954. For research like this is that in 1968 he was the first recipient of the prize named after Ettore Majorana, his ill-fated colleague and friend of his years at the Institute of Rome. Well, if I can spend these minutes remembering Giancarlo Wick, it is precisely because 70 years ago he proposed an idea that has become one of the paradigms of collision theory. Obviously, it is a minor but very important result for our area of research, and in all fairness, it is called Wick's argument. While Wick raised this argument in 1852, he did not write or publish it. To find it, we must go to a note added in the Gallic proof of a 1953 paper by Jackson and Schiff. There, the authors claim that Wick pointed out to them that in an electron capture collision the internuclear interaction would give a negligible contribution, and that it can therefore be eliminated from the Hamiltonian. That in the 1950s someone came to tell that a term could be removed, reducing the effort and calculation time, was happy and important news, for the simple reason that there were no computers and everything had to be done analytically at best and by hand at worst. Of course, if this argument was good for electron capture, it was also good in virtually any other case, such as excitation or ionization, given the provision that the projectile should have to be a heavy particle. And the latter is very important, since Wick warns us that this approximation is valid in a range of the order of the ratio between the mass of the electron and the mass of the ions involved, and so we continued from then on. But Wick's argument does not end there. He goes on to propose that we can consider the nuclei to be infinitely heavy and configure the problem as an impact parameter calculation. And we do follow this advice, we really do. A vast majority of the theories we use to analyze heavy particle impact collisions assume that the projectile follows a classical rectilinear and uniform trajectory. It is fair to say that this second, even stronger approximation was far from being new, since it had already been proposed more than 2 decades earlier, in 1830, by Cohen-Brickman and Hans Kramer, as we can see in this figure extracted from their original paper. And finally, going back to Wick's argument, he says that the internuclear interaction can be removed from the Hamiltonian by an appropriate canonical transformation. And when we talk about the Hamiltonian, we are basically talking about a modification of the quantum state, solution of the Schrödinger equation, in the transition matrix. Thus, we have these 3 approximations, which are at the basis of the vast majority of our current calculations, and which we use almost without thinking about them, much less questioning them. And everything is well if what we are doing is calculating total cross-sections. We can even calculate ionization cross-sections differential in the energy and angle of the emitted electron, in what we call electron spectroscopy, and everything will be okay. And this was all there was to measure, and therefore to calculate, for many, many years, until the experimentalists tried to ruin the life of us poor theorists with the new technical skills, which allow them to measure, for example, the deflection angle of the projectile. Well, if the projectile is deflected, one would think that there is no way to maintain Wick's argument. How can we possibly maintain the hypothesis that the projectile follows a rectilinear and uniform trajectory if we want to study its deflection? It wouldn't seem to make no sense, wouldn't it? And here, the epistemology of Imre Lakatos enters the scene. In 1870, he explained that each theory has a hard core of assumptions that cannot be abandoned or altered without abandoning the theory altogether. Thus, when something appears that threatens the hardcore, a patch is attached to the theory. These so-called auxiliary hypotheses are considered expendable and may be altered or abandoned as empirical evidence required in order to protect the hardcore. And this is precisely what happened to the theories based on Wick's argument. Of course, measurements including a projectile deflection were considered as red flags. But if that angle remained at a reasonably small values, that is, in the order of the ratio between the masses of the electron and the projectile, everything should be fine. This defense of the hardcore of Wick's argument required the inclusion of several auxiliary hypotheses. The most common was to continue using the model as it was, but associating a classical deflection angle to each impact parameter. Let's see how it works in a specific case. So let us study the double scattering mechanism in electron capture collisions proposed by Lewis Hill Thomas in 1927. This is a diagram of this mechanism that I took from the book of Blanston and McDowell. Let's mention that being 30 years old, this book, that every self-respecting theorist has surely read, can already be considered a classic. Since Thomas' angle is of the order of ratio of masses, everything should be okay with the theories based on Wick's argument. Well, maybe not so. In this figure that I also took from this book, only one of the curves corresponds to a theory based on Wick's argument, and it is precisely the one that less coincides with the experimental data, and does so in a logarithmic scale. In these last 3 decades, there have been many advances, and the agreement has certainly improved. But as we increase the scattering angle, the comfort zone of Wick's argument fades away as the gradient in violet. So what would happen if we took this scattering angle to the limit and beyond? Let me show you these experimental results obtained more than 2 decades ago by our colleagues from Debrecen. They correspond to the ionization of argon by the impact of 75 keV protons. Here the projectile and the electron end at the same angle at 3.7, 5, 6.8 and 8.1 degrees. In the lower part of the second figure, we also see the case where the electron is measured in the forward direction and the proton at 6.8 degrees. The performance of the continuum distorted wave model with the impact parameter approximation would be even worse than shown here. But it was not so, since the authors used a broken line approximation in which the straight projectile trajectory was replaced by its 2 classical asymptotes. This provision improved the agreement, but clearly was not enough. There has also been an attempt to use a hyperbolic trajectory, but the results were not better, and as far as I know, they were never published. And these are the results obtained by using a CDW model which does not employ any of the approximations suggested by Wick's argument. This model not only reproduced very well the form, but also the scale of the experimental data, and without including any artifice. The obvious conclusion should be that when dealing with the projectile scattering angles, Wick's argument should be ruled out, even for deflection at a small fraction of a milliradian. But as Kuhn and Lakatos shown us, this is hardly the case. Here we see a very recent comparison of the standard CDW models with some experimental results by our colleagues from Missouri-Rolla for the ionization of helium by the impact of protons of 75 keV. We show the fully differential cross-section as a function of the electron energy when the electron is emitted in the forward direction and the proton at a very small angle of 0.5 milliradians. The performance of the CDW models with Wick's argument represented by the green and red lines is very poor. The blue line, which does not do very well either, is another type of theory. Let's move on to another problem in the face of which Wick's argument seems small and simple. We can say that in our area of research, Coulomb's potential is everywhere. However, the scattering theory, as we know and use it, is not applicable to that potential. We learn to patch here and there and walk on the razor's edge, but the problem remains. It happens that on the same foundation of the theory, this asymptotic condition is imposed to the acting potentials, which obviously the Coulomb potential does not fulfill. This is not the place or the time to get into the details of the problem, but we can at least propose a classical analog. The scattering theory requires trajectories to be asymptotically free, and that never happens with hyperbolic orbits. The first mathematically rigorous demonstration that it was possible to construct a scattering theory that admitted Coulomb potential was made by John Dollar as part of his doctoral thesis and published in 1964. However, his result was impractical, since although it managed to reconstruct an essential tool of the theory, which is the so-called Moller operator, it remained in the form of a limit in time. The solution to this problem was provided in 1976 by Van Haringen, also in connection with his doctoral thesis, which he presented 2 years later. Basically, Van Haringen demonstrated that the scattering theory can still be used in the usual way, but by evaluating the transition matrix of the energy shell and taking the on-shell limit at the end of the calculation, not before. The prescription to perform the calculation of the energy shell seems somewhat bizarre. But if we think about it, it should not be so strange after all. Consider that instead of having the projectiles, gun, and detector at infinity, we bring them closer to the target. In that case, how the potential acts at infinity is totally irrelevant if, of course, it vanishes there. Note that the price to pay in exchange for this trick is that now, the initial and final kinetic energies do not match the total energy of the problem. Well, then, my Haringen proposal is to calculate the cross-section and then take the gun and the detector back to infinity. I would like to emphasize that in what I have told so far, there is no argument, conjecture, or approximation. This is a rigorous generalization of the usual collision theory that can be applied in the case of long-range potentials and that, notably, only implies being very careful in the order in which things are done. First, do the calculation of shell and then take the on-shell limit. It can also be rigorously demonstrated that within this framework, perturbative expansion as the distorted wave or Born series are valid and feasible to do. And furthermore, that it is possible to extend this theory beyond the simple elastic scattering to the case of multi-channel collision, that is, excitation, electron capture, ionization, etc. Everything seemed to be going okay, but many years ago, there was a contentious point regarding another method to deal with Coulomb potentials, which was and still is widely used. It basically consists of incorporating the correct boundary conditions, which is a simple and promising idea. Asymptotically, Coulomb states differ from plane waves in a logarithmic phase. So, to correct the scattering theory, that aconal distortion should be incorporated in the calculation. But beware, for everything to fit, it is necessary to simultaneously incorporate the corrective potential. If not, this conjecture fails. This conjecture has been proposed by Mulherin and Sainz in 1970. As in the case of Dollar and Van Haringen, this article was also published in the Journal of Mathematical Physics, and again based on the thesis of its author, Denis Mulherin, who unfortunately passed away very recently, November 21st last year. But at that time, not everybody were happy with this conjecture, and the strongest and most substantiated attack came from all the people from the founder of this line of research, John Dollar himself. Already in the title, in addition to misspelling Mulherin's name, Dollar emphasizes that the proposal to use correct boundary conditions was what it really was, a conjecture, since its validity has not been demonstrated so far, and on the other hand, he believed that it did not have a straight physical interpretation. Other shortcomings of this conjecture were that it had not been rigorously demonstrated, as in the case of shell theories, that it was possible to perform perturbative expansions, nor that a generalization to multi-channel collisions could be constructed. And all this was very serious since most of the continuous distorted wave theories are based on these three fundamental pillars. Fortunately, in 1989, we showed that the Mulherin and Sainz conjecture could be deduced from Van Haringen formalism, that ceasing to be a conjecture and becoming a rigorous theory. I must confess that in my youth, a long time ago, I devoted a lot of time and effort to see if it was possible to use the correct boundary condition theory to rigorously construct perturbative expansions and generalize it to the case of multi-channel collisions. But sadly, I didn't make it. In the more than 3 decades that have passed since then, I don't know if anyone did. Finally, I would like to share a sign of attention. The demonstration of the validity of the Mulherin and Science theory that we developed with Masek was based on an equation known by several names. And it was essential for the demonstration to show that this additional term was exactly zero. So if you are going to reincorporate this term into a continuous exotic wave theory, keep in mind this fact, please. Well, to conclude with this talk, let me go back to the off-shell theory. This rule does not seem too difficult to achieve, but as always there is a catch, and it is a trap of enormous proportions. What happens is that while these limits are well defined for potentials that meet the asymptotic condition, this does not happen with the Coulomb potential. In fact, the transition matrix presents a branch cut on each of these planes. That is, depending on whether we approach the surface from one side or the other, we will obtain different results, and different from what we would have obtained if we had calculated the transition matrix exactly on the surface. Let me show you what is going on with an example where we evaluate the ratio of the off-shell and on-shell transition matrix element for a cut-off Coulomb potential of range R. As we can see, while the potential remains shielded, this ratio is continuous and, unsurprisingly, tends to the correct value when the initial and final impulses are equal. However, for the pure Coulomb potential, it tends to different values as it approaches the on-shell boundary on one side or the other. Why is this important? Well, obviously because we must take these anomalies into account when applying the off-shell theory. But there is another, more important motive. And it is that in absolutely all our theories for multi-channel collisions, such as excitation, capture, or ionization, the Coulomb continuous states are off the energy shell. However, we approximate them by their on-shell versions. Let me be more specific. Any multi-channel problem can be reduced to a succession of two-body events. However, these basic building blocks do not correspond to elastic processes but are off the energy shell. In view of this difficulty, distorted wave models include a subsidiary approximation where these off-shell terms are arbitrarily forced to lie on the energy shell, as shown here. At the first glance, since the energy deficiency is negligible for high enough velocities, the on-shell assumption seems to be completely justified. However, as we have seen, for the case of Coulomb interactions, the two-body off-shell distortions have branch point singularities on the on-shell limit. Can these anomalies be included in the theory? If so, do they produce a sizable effect? The answer to both questions is yes. We know exactly and analytically how off-shell states behave at this limit, and it is not so difficult to include them in our models. As far as I know, the first to take these anomalies into account were Masek and Knut-Tolfer in 1885, showing that the incorporation of off-shell anomalies improved the impulse approximation, leading it to have much better agreement with experimental data. For our part, we applied this technique to the formation of positronium using an agonal final state continuous distorted wave model, and when compared with experimental results, the improvement achieved by incorporating the off-shell anomalies was really dramatic. Another good news is that, in many cases, this effect can be included as a multiplicative factor that corrects the usual theories. Here I show you what this factor would be like for a collision of carbon nuclei against atomic hydrogen, depending on the energy of the projectile. Note that it produces an increase in the cross-section of up to 60% at high energies and a significant decrease for low energies, a result that confirms what was found by Masek and Tolfer in the original article so many years ago. And that's it. In this presentation, I have tried to review, not as a criticism but as a trigger for reflection, some of the paradigms that we incorporate into our theories, sometimes knowingly and sometimes without realizing it. Thank you very much for your attention.